Hi everyone, welcome to lesson 6 of our trigonometry unit. Today's lesson, proving trigonometric identities, so we're proving identities. Before we get there though, we're going to start on our opener question. It says, the exact value of cos pi over 12 can be written in this form, radical a plus radical b divided by c. What's the sum of a, b, and c once you have it solved? So first off, I'm going to work with this pi over 12. I have no idea what it is, hypothetically speaking, what it is. So let's switch it over to degrees, something that we can evaluate even better. So I can say something like cos pi over 12 is equal to cos 15 degrees. Okay. From here, 15 degrees is a bit easier to evaluate. I know that I can create 15 degrees by going cos 45 minus 30. If I have this set up, I'm going to quickly rewrite cos 45 minus 30 as cos 45 cos 30 plus sine 45 and sine 30. From here, I evaluate each individual trig function. And so here, cos 45 is the same thing as root 2 over 2. Cos 30 is the same thing as saying root 3 over 2. Plus sine 45, so sine 45 is root 2 over 2. And sine 30 is 1/2. From here, I'm going to multiply my fractions basically together. On the left, I get root 6 over 4. On the right, and we're going to go plus sign plus root 2 over 4. Let's simplify that all together. So this is now root 6 plus root 2, all divided by 4. And here we have the format that the question gave us. Root a plus root b divided by c. So if I took a plus b plus c, we get a value of 12, and 12 was what I was looking for overall. In today's lesson, though, we are proving trig identities, so what we want to do is basically build a chart. And on our chart, we want to create a left side versus a right side chart. What you're going to do is you're looking for obvious substitutions right away. So anything that you see that your gut feeling says, hey, maybe you should switch it out or switch in for a basic identity, you might want to do that. Remember that identities can be rearranged if needed. You're going to start on what you consider the complicated side first. Your goal is to make it equal the other side, whether that means you're working on the left side first, making it equal the right side, or the right side first, making it equal to the left side. Usually we write everything in terms of sine and cosine. So if I saw a tangent or cotangent, I'd write it in terms of a sine and a cosine. Write expressions with fractions as a single fraction. So again, that just means clean up all your fractions. Look for common factors, multiply by conjugate if necessary. So that means if you had a radical in your denominator, a binomial radical, you want to multiply by the conjugate to get it out of there. And constantly consult your formula sheet, and that's going to be key here because you're going to be using your formula sheet quite a bit. So make sure that you have it available and ready to kind of consult. So, example 1. Prove the following. So we have secant squared x divided by cos squared x plus 1, and we want to equal secant squared x. Sorry, and that was sine squared x, that is. So here, can I rewrite this somehow? Well, I know that sine divided by cos is the same thing as tangent. So if I rewrote this in terms of tangent, let's see if that helps me. So here I have tangent squared x plus 1, because we haven't touched that 1 yet, is equal to secant squared x. Well, I'm going to consult my formula sheet here. I'm looking for something that says tan squared x plus 1. In fact, there is something that says tan squared x plus 1. It's about a third of the way down on the right hand side of your formula sheet. It says 1 plus tan squared x equals secant squared x. So here I can rewrite this as secant squared x equals secant squared x. So here we built a left side that equals a right side, so our proof is complete. Could you have proved this a different way? Of course, you can prove this in a different manner, and I'll do it. I'll give you another option right here. So in this example here, what if we wrote everything in terms of a fraction? So if I had sine squared x divided by cos squared x, 1 I'm going to rewrite as cos squared x divided by cos squared x, because that's the same thing as 1. And secant, of course, is the same thing as saying 1 divided by cos squared x. From here, let's see if we can simplify anything. From here, I have common denominator. So what do? I just add my numerators together. So my numerator is going to be sine squared x plus cos squared x. All of that is now divided by cos squared x. And we're hoping to get to 1 over cos squared x. In the numerator here, sine squared x plus cos squared x, this is one of your trig identities. This is your Pythagorean identity. It says here on your formula sheet again, sine squared x plus cos squared x is equal to 1 there. So I can rewrite that as 1 over cos squared x, and that does match up to our right side of 1 over cos squared x. And there we go, we have a left side equaling your right side again, so our proof is complete. In example B, what I consider the easier side is the right side. I want to match up my left side to equal 1, so let's see what we can do. So first off, I see cotangent squared x. I don't like the cotangent written there. I want to write it in terms of sines and coses, so let's rewrite that. So here I have sine squared x plus sine squared x, but this time, instead of saying cotangent, I'm going to say this is the same thing as saying cos squared x divided by sine squared x. And all of that is now still equal to 1. From here, I see sine squared x and a sine squared x. These will cancel out. I'm left with sine squared x plus cos squared x equals 1. And of course, again, this here, sine squared x plus cos squared x, that's your Pythagorean identity. So that's the same thing as saying 1. That's equal to 1. So I can say left side equals my right side. So now my proof is complete. In the next example, example 2, we have proved the following. And here, there really isn't a good side that you necessarily need to or want to start on. It doesn't matter which one you do. For me, I'm just going to try my best to match everything up to the right hand side there. So what am I going to do? On this left hand side here, I see a 1 minus sine x. I can't really work with that, so I'm going to multiply that by its conjugate. So I'm going to rewrite the left side as follows. So I have cos x over 1 minus sine x, and I'm going to multiply that by its conjugate. So let's multiply by 1 plus sine x over 1 plus sine x. And multiplying by your conjugate, again, just a reminder, really shouldn't do anything to your equation. This is really multiplying by 1. 1 times the original does not affect anything. Equal sign is here. You have 1 plus sine x over cos x still on the right there. From here, let's see what happens when we multiply this. So again, there should have been a bracket here, a bracket right here. This would be a distribution of a monomial times a binomial. Down here is a binomial times a binomial. So up in my numerator, I'll have cos x, and I have that 1 plus sine x. I don't really want to distribute it just yet because I want to take a look at what my denominator is before I distribute it. In my denominator, this is 1 times 1, which is just 1. 1 times sine x, which is positive sine x, negative sine x, those will cancel out. I have minus sine squared x left over here is equal to 1 plus sine x over cos x. In my denominator here, again, if I look on my formula sheet, I do notice something that says 1 minus sine squared x. It's not really there. It's your Pythagorean identity rewritten. This is the same thing as saying cos x in your numerator, 1 plus sine x in your numerator. My denominator is rewritten as cos squared x. There we go. Again, we still have the 1 plus sine x there on the right, all divided by cos x. And we wanted a cos x in the denominator somehow, so this does match up now. Here though, I can quickly clean up. This numerator cos x will cancel out with that exponent 2, leaving you with a single cos x in the denominator there. So now you have 1 plus sine x in your numerator divided by cos x denominator, and that's going to equal on the right side the 1 plus sine x over cos x. So here again we have our left side equals our right side, which concludes the proof on this first one here. In the next example here we have secant theta multiplied into 1 plus cos theta, and we're hoping to get 1 plus secant theta overall. So again, this right side here looks a bit easier. It looks a bit cleaned up already, so this left side is what I'm going to work with. So secant, I'm going to rewrite that as 1 over cos theta, and that's going to be multiplied by 1 plus cos theta. We're hoping we get to 1 plus sine theta, or sorry, not sine, but 1 plus secant theta there. My apologies. Here, if I distribute in, I'll end up with 1 over cos theta plus a cos theta divided by a cos theta. And again, we're still hoping to get to this 1 plus secant theta. Well, of course, 1 over cos is the same thing as saying secant theta, and cos over cos is just 1. And so there you have it. This is basically the same equation. I'm just going to quickly do a rewrite so that we do match up. I switch positions on the left here. That's equal to 1 plus secant theta. So therefore our left side does equal our right side. And there we go. That's example 2.